So today we're going to talk about atomic models and electrons. In your discussion with the atomic history, you talked about the different theorists and what they contributed. And towards the end of your timeline, you talked about Schrodinger and Heisenberg. And the quantum mechanical model was discussed. So the quantum mechanical model restricts the energy of electrons to certain values and certain energy levels. And you're going to find out that that's actually the way the periodic table is arranged. The periods on the periodic table correspond to the energy levels. However, the quantum mechanical model does not, let me go back here, does not specify exact paths the electron takes around the nucleus. Electrons are located in what are referred to as electron clouds. So the electron clouds in the quantum mechanical model are areas where there's a high probability of finding an electron. And when you visualize these clouds, they are fuzzy looking regions that appear when you take a scanning electron microscopic images of atoms, and where they are more dense, that's the higher probability regions where electrons can be found. So here's a picture of Schrodinger's model, and the darker regions here are where there was a higher probability of finding an electron. Closer into the nucleus, it's almost clear looking. There's no electron density at all close in next to the nucleus. And here's a pictorial that shows a diagram of a Bohr model. And in the Bohr model, he does have the electrons, and he was right in that the electrons are in discrete energy levels. They are more apt to only possess certain energies and be located, but the first two only possess enough energy to move so far out away from the nucleus. So that part of his theory is correct. However, so even with the electron cloud model, we know that there's probably only going to be 2 electrons that are going to be in this region. But we know that they don't move in a circular orbit, a discrete orbit like Bohr thought. That they're moving around in just a region, not a discrete path. Bohr did have the right idea, though, about the different energy levels, and again, that's how our periodic table is arranged. The first energy level is the first period on the periodic table. So energy level 1 is period 1 on the periodic table. So the first period is hydrogen and helium, and hydrogen has 1 electron, helium has 2, and that corresponds to the first energy level. Okay, atomic orbitals are represented pictorially as a region of space in which there is a high probability of finding an electron. There are 4 different types of atomic orbitals, and only 2 electrons can occupy an atomic orbital at any given time. So if you have an atomic orbital, there's only a maximum of 2 that can ever occupy an orbital, and they have to be spinning in opposite directions. So the next slide, in the first energy level, we only have one type of orbital, and that's a 1s. In the second energy level, we have 2 different types that can be in the second energy level, and that's an s orbital and then a set of p orbitals. And I've got all this written on the next slide for you to take down. In the third energy level, there's 3 different types, S, P, and D. And in the fourth energy level, there's S, P, D, and F. So there's 4 types. There's S, P, D, and F type of orbitals. That's the 4 types of atomic orbitals that electrons can be held within. Okay, and these are the different subshells. So this is what I want you to take down instead of just that table. An S subshell is a single orbital that can hold at most 2 electrons. P subshells consist of 3 orbitals, and each one of these can hold 2 electrons, and that gives you a total excuse me, of 6 electrons. The D subshells consist of 5 atomic orbitals. Each one of these can hold 2 electrons for a total of 10 electrons. And then the F subshells consist of 7 orbitals, and each one can hold 2 for a total of 14. Okay, let me show you a picture of the s orbital. The s orbital, the first energy level s orbital, is small and surrounds the nucleus. The second s orbital on the second energy level is larger than the first, and it is completely surrounding the first energy level. Then the third energy level, of course, is bigger. It's surrounding the second and the first energy level. But if you notice, they all have that it's just a round circle, a spherical shape. The p orbitals are dumbbell shaped. So you've got 1, 2, 3 on the x, y, and z axes. And then when you put them all together, they kind of clump together and form this, I don't know, kind of a, I don't know if it's a flower shaped or what, but there's one on the x axis, one on the z, and one on the y axis. Then the d orbitals, you've got 4 of these kind of flower shaped sets, and then 1 with a dumbbell and a donut in the middle. That's what the 5d orbitals look like. So there's a set of 5 for the d, and then there's 2 little electrons moving around in this area around the nucleus. And then the f orbitals are in these configurations. There's 1, 2, 3, 4, 5, 6, 7. So there's 2 electrons moving in between each one of these configurations. And that's some nuclear physicist came up with all these, the mathematical calculations to describe how these electrons are moving around in all these. So Schrodinger and then some other highly intelligent individuals came up with all these calculations to describe how these electrons are moving around in all these locations. So it's way above my head, and I could not even begin to draw these. So I just wanted to show you these pictures, but that's how the electrons are arranged around the atom. Now, we have special rules that we have to go by when we're talking about placing electrons around the nucleus of an atom. So when we're drawing out or writing out the electron configurations for an atom, we have, first of all, we've got 3 rules that we have to go by. The first one, the off-ball principle, states that we always put 1 electron into the lowest energy level, the first available orbital before 2 electrons occupy the same orbital. 1 electron goes into the lowest available energy level before we go to the next. Pauli exclusion principle states that each orbital can hold a maximum of 2 electrons, and they must have opposite spins. Then Hund's rule states electrons occupy orbitals of the same energy in a way that makes the number of electrons with the same spin direction as large as possible. That means everybody gets their own place. If we've got say a set of D orbitals that we're putting electrons in, everybody gets one seat on the D bus before anybody pairs up and sits with somebody else. Every D orbital gets at least 1 electron before we start pairing up. And we're going to do some practice. This is why it was important for us to be able to do what you just tested about last week to figure out the number of electrons in an atom, because that's the first step. We have to know how many electrons are present in an atom before we can go forth. All right, then we're going to use this electron filling chart to guide us, and I'm going to go ahead on this example. We're going to I've got this right here that we're going to use. If calcium has 20 electrons, and if we look on the periodic table, calcium has an atomic number of 20, so that means it has 20 protons. That means it also has 20 electrons. So we're going to use this electron filling chart, and the first place that we're going to put electrons is the 1s orbital. All s orbitals can hold 2 electrons. So 1s, and I'm going to write 2 here as a superscript because that's how many electrons an s orbital can hold. Then I'm going to follow my arrows to the next available orbital, and that's the 2s orbital. 2s. And again, all s orbitals can hold 2 electrons. All these little superscripts have to add up to 20. After 2s, I followed my arrow. I go to the next available orbital, and it's the 2p orbital. 2p's Any p set of orbitals can hold up to 6. So I'm going to put 2p and I'm going to put a little 6 here because I can put up to 6 electrons in an s or in a p orbital. So I've got 2 plus 2 is 4 and 6 makes 10 at this point. After the 2p, I'm going to follow my arrow and it leads me to 3s. I write down 3s. Any s orbital, I can put 2 electrons in, so I'm going to write a little 2 here. Now I'm up to 12. After 3s, I come over here to the end of my arrow, follow it down. I'm at 3p. I write down 3p. In all p's, I can put a maximum of 6. So now I am at 18 and I need to get to 20. So I follow the 3p down to 4s. 4s, and I can put 2, and that takes me where I need to be, 20 total. So when I add up all these superscripts, if I've got 20, I'm done. Second example, carbon. Carbon, I look on the periodic table, and it has an atomic number of 6, so that means it has 6 electrons. So I start up here at the top, 1s, all s's can hold 2. I go to my next orbital, and it's 2s. Oh, I am so wrong. I made a mistake. 2s cannot hold 4. That should be 2. And then after 2s, I'm going to go, and that's 2 plus 2 is 4. And then after 2s, I go to 2p. Now, that is 4, so I need a 2. And I need to make that my, don't need to do that, I need to make it a, okay, sorry about that. All right, and then nickel. Nickel is element 28, so it has 28 electrons. And we're going to start again with the first energy level. You always start with 1s. It can hold 2. You go to 2s. It holds 2. You go to 2p. It holds 6. Go to 3s. It holds 2. Go to 3p. It holds 6. After 3p, we go to 4s2. And then after 4s, we go back over here and we're in 3d. And that's 10, that's 20, and then we need 8 more. We put an 8 there. That's 28. All right, that is the example, and that will be it for today. We'll do some example problems. We'll have some to work on.